This is overall the 5th video on convergence and divergence tests for BC Calculus, but it's the 2nd video for part 2 of our notes. So in this video, we're going to be looking at the limit comparison test. The previous video was about the comparison test. This one's about the limit comparison test. So we looked at, in the last video with the comparison test, the sum from n equals 1 to infinity of 1 over 2 to the n plus n. And we figured out by comparing it to just 1 over 2 to the n that it would converge by the comparison test. This one, we're looking at the sum from n equals 1 to infinity of 1 over 2 to the n plus 1. Well, we would know we could compare this one to 1 over 2 to the n as well. 1 over 2 to the n would always have larger terms. It's the b sub n series then. It converges, so therefore this guy right here would converge by the comparison test. What about, though, 1 over 2 to the n minus 1? Well, for this one, this guy would have terms. If we write out some of his terms, starting with n equals 1, we would get 1 plus 1/3 plus 1/7, and so forth. Well, 1 over 2 to the n is 1/2 plus 1/4 plus 1/8. So this doesn't work the same way as the others do because this 1 over 2 to the n minus 1 is actually larger term by term than 1 over 2 to the n. So this would be our b sub n series. And we can't do the comparison test that way for convergence if the series we're looking at is our larger series. We can only use it then to show divergence, which won't work. So another option that we have for determining whether or not 1 over 2 to the n minus 1 converges or diverges would be the limit comparison test. So the way that the limit comparison test works is that if you have two series, a sub n and b sub n, and it does not matter which one's larger, which one's smaller, just two similar series. And we know that both a sub n and b sub n are, well, the a sub n is greater than or equal to 0 for every term, and b sub n is greater than 0, so it can't have any 0 terms for all n from 1 up. The limit comparison test says that if the limit, that's the name of the test, as n goes to infinity of a sub n divided by b sub n is positive, so the limit of the ratio has to be positive and finite. That means I have to actually get an attainable value. So like infinity is not an answer. Then what that means is that both the series, either, whatever they do, they both do it. So they either converge or both series diverge. So how is this helpful? Well, let's look at the 1 over 2 to the n minus 1. We know that we can compare it to the sum from n equals 1 to infinity of just 1 over 2 to the n because they are similar in nature. And I know that both of these always have positive terms. So it really doesn't even matter which one's the a sub n and which one's the b sub n. You could do your ratio the other way from me, and it's all going to work out. But since I do know from the ratio test that this guy converges, then if I take the limit of the ratio of these two guys and I get a positive finite answer, then that means that my original series also has to converge. Now, if I knew that 1 over 2 to the n diverged, and I still got a positive finite answer for this limit, then that would mean that the guy that I've underlined there with the squigglies would also diverge. They have the same behavior in terms of their sum, is what the limit comparison test shows us. So I'm just going to take the first guy they gave me over the one that I'm comparing him to. Like I said, you could do it in the other order though. It'll work out. So I would have the limit as n goes to infinity. So if I do my whole keep, change, flip, I end up with 2 to the n over 2 to the n minus 1. Now, if I try to substitute infinity into that right now, I get 2 to the infinity over 2 to the infinity minus 1, which is infinity over infinity, which is indeterminate. So, L'Hopital's rule. So that would equal the limit as n goes to infinity. Now, 2 to the n is an a to the u derivative. So it's a to the u times the natural log of the base. Same thing on the bottom, a to the u times the natural log of the base. And then the minus 1, his derivative is just 0. So notice the derivatives turn out to be exactly the same. So this actually ends up being the limit as n goes to infinity of 1. So my answer is 1, which is positive and finite. It is an actual number. So both of those conditions were met. So we could say, therefore, the sum from n equals 1 to infinity of 1 over 2 to the n minus 1 converges by the limit comparison test with the sum from n equals 1 to infinity of 1 over 2 to the n, which converges by the ratio test. So I do need to state how I know that the 1 over 2 to the n would converge. And we previously did the work on why we knew that converged, but I would want to include it in this problem as well. I would also have to have included in either in my steps or in this sentence down here the fact that my limit was positive and finite. You need to say those words in your work in order to be able to apply that stuff to the limit comparison test, because you're basically stating your conditions and the fact that the conditions are met. And then you want to summarize which test you used and how you knew that it either converged or diverged. If you don't have your explanations written out for these problems, you're not going to get credit for your answers, because all we know is that you made a 50-50 guess as to whether or not it converges or diverges. Okay? So that wraps up the limit comparison test, and that ends part 2 and our 5th video on convergence and divergence.